I want to thank the organizers for such an in-person meeting and giving me the opportunity to speak here. Needless to say, I'm really glad to be back. And today I will talk about quantum circuit and collisions in the black hole interior. It's based on a couple of papers with Felix Hill and Alex Stryker, as well as some ongoing work that hopefully will appear very soon. Okay, so first of all, I want to give some motivations. It's well known that two distant black holes can be connected in the interior through a wormhole. And such an Einstein-Rosen bridge can be interpreted as an entangled state. This is a famous statement of ER equals CPR. But this also poses a small mystery, because two signals sending from the two different boundaries can meet in the interior. On the other hand, from boundary point of view, there are no boundary interactions. So what governs the law according to which the two signals interact? And in particular, I want to consider two cases. In one case, as on the left panel, there are two signals, the red one and pink one. They both come in from the right boundary system. And in this case, the two signals, one comes from the left boundary, the other one comes from the right boundary. But if we trust the box geometry, the signals should interact in the same way, no matter if they come from the same boundary or come from two different boundaries. This is required in gravity, but the boundary mechanism is not clear. And in this talk, we'll try to understand this from point of view of quantum circuit. I want to point out that there are recently some very interesting papers exploring related issues from different perspectives. So here's the outline of the talk. We will review a meeting in the interior of wormhole and overlap of perturbations in the quantum circuit. In particular, we will look at overlap in the quantum circuit and compare this with the post-collision geometry. First, for ADS-sized black holes, we will compare the two cases where for the collision signals coming from two different boundaries or the same boundary. And we will discuss collisions with localized shocks. At the end of the day, I will point out some future directions and unanswered questions. So first, Bulk tensor network and quantum circuit. It was argued that the bulk geometry reflects the minimal circuit preparing the state. And here is the time evolved thermal field double. I mean, you have a bunch of bell pairs, and then right time increases this way, left time increases this way, and you can apply this unitary. So these orange dots represent unitary operators. They represent gates acting on the circuit. As the circuit gets longer, the interior geometry also gets longer. And notice that in this particular setup, this gate has have the property that they can be undone from either. Yes, please.
Can you talk about the collision behind the horizon of thermal field double?
Yeah.
So from the boundary point of view.
Yes.
So it will take an infinite time from the boundary point of view, the perturbation sense reaches the event horizon.
That's true.
But then how do you talk about the collision behind the black hole horizon from boundary point of view?
We'll talk about that later. Okay, so from this, so we notice that these orange gates have a property that they can be undone from either side. So roughly speaking, equivalent way to say this is that these gates, they do not change the density matrix of either A and B. And so in no sense, they can belong to either subsystem or A and B. In fact, they belong to the union of A and B. And this property has a boundary, as a bulk interpretation that as we apply this kind of gates, this thing is the Einstein-Rosen bridge is getting longer, but notice that the part is getting longer is actually outside the entanglement wedge of A and also outside the entanglement wedge of B. It's only in the shared interior region, which belongs to the union of A and B together. So the key property is that entanglement gives rise to shared quantum circuit. Let's look at perturbed thermal field double for ADS-sized black hole. I mean, we argue that this orange gates has a property that they actually belong to shared A and B together, but we can ask that are there gates that do not satisfy such property? Yes, there are. For this purpose, we need to consider that, let's say we send in some extra perturbation, say for example, from left side, and such perturbation would increase the coarse grain entropy of the left black hole. And in order to represent this increase of coarse-grained entropy, we introduce the extra qubit that come in at a particular time. We imagine this one carries some disease and spread out exponentially in time, as we all know too well these days. And so this red gates, because they involve this extra qubit, so they can be no longer undone from the right side. But notice that because this perturbation actually takes some time to spread to the entire system. So even after this perturbation comes in, there are still some of these orange gates that belong to A and B shared together. And correspondingly, I mean, they are still correspond to this part of geometry that is the orange part. It's shared interior, but it's after the red perturbation.
Ying, can I ask you a question?
Yes.
Is the vertical direction in your diagram time, or is it just qubits?
Vertical, you mean in the circuit diagram?
Yeah.
Vertical direction. Okay, good question. Vertical direction in this case doesn't mean anything. It's basically just put down all the. We don't understand. So this circuit, roughly speaking, corresponds to a region in the bulk that has a extent of ADS distance, and how this is related to arrangement of these qubits, this circuit in vertical direction, we don't understand. But for later discussion, when I introduce localized collisions, the vertical directions will be transverse direction. But for now, no, we don't understand how this arranged to give rise to time in the bulk.
But it's a snapshot at a given time.
Yes.
Okay.
So in this talk, we'll be interested in the collisions. Consider a quantum circuit with perturbation from both sides. Let's first consider ADS size black hole, basically minimal size of black hole. And when you draw the quantum circuit, you'll see that there are different cases with the difference that in the time arrangement. When PWR is larger than minus WL, the two perturbations do not have overlap in the quantum circuit. Correspondingly, we want to say that the signals stand into the bulk heat singularity before they have a chance to meet in the wormhole. A more interesting situation is that actually the two signals do have some overlap in the circuit. What we mean is that there is a certain portion of a circuit within which both perturbations appear. And it's intuitively clear that, so we want to say that in this case, the perturbations will actually, the signals will actually collide inside a wormhole. And it's to be intuitively clear that the larger the overlap is, the stronger the collision is. And one can make this more quantitative by, say, one can actually diagnose the happening of a collision by looking at the size of the operator preparing the state. This computation reduced to a computation of a particular 6-point functions. If you are interested, you can look at a paper, but I'm not going to talk about it in today's talk.
I have a question.
Yeah.
So in this picture, if
Yes.
I move the right time to the left much and this time to that direction very much, then you may have some range overlap,
Yeah.
right?
Yes.
Not just overlap in this way, but even overlap in this way, right?
Yes, exactly.
But okay, then qualitatively, what will happen for the right picture?
We will see later in later slides. Yeah. So let's so in this talk, we won't talk about, say, about diagnosing the collision. Instead, one quantity we'll be interested in is about the space-time geometry after the collision. And we want to compare this with certain properties of the quantum circuit, in particular, this overlap region of the quantum circuit. And as we argued before, there are still potentially, there might be some healthy gates here. And this healthy gates should be, say, in the shared region and also be after the both, it should be behind both perturbations. So we want to identify this orange gates, this healthy gates in the overlap region with the post-collision geometry. And so it should be clear that basically this entire setup, everything is only a function of delta t, where delta t characterizes how large overlap is. From quantum circuit point of view, this is a result of translation symmetry of quantum circuit. From bulk point of view, this is just the boost symmetry. And So recall that the goal is that we want to compare boundary and bulk quantities. The boundary quantity is about some circuit property, in particular the overlap region. The bulk quantity is the post-collision geometry. Let's first do some very rough circuit analysis. So for purpose of later discussions, we will consider the case where actually the two scrambling times are significantly different. The way we set it up is that we make the initial size quite different. For example, we can set the initial size of the first perturbation to be of order 1, the second perturbation to be order square root of s. When they set up the scrambling time for the first perturbation will be roughly twice of the scrambling time for the second perturbation. And we use this picture to represent, let's say, their overlap. Let's say the red signal come in, propagate towards the left. The pink signal come in, propagate towards the right, and there is some overlap delta t. And this is we call t star 1 is the first scrambling time. This we call t star 2. The first regime is when delta t is less than the smaller of the two scrambling times. It's clear that the healthy gates is basically this part, and it should, roughly speaking, grow linearly in delta t. Another regime is when, let's say, when delta t is, another regime is when delta t is, let's say, is between the two scrambling times. And in this case, you can see that actually, so the overlap region, healthy gates in the overlap region is roughly speaking is in this part. But this part actually no longer depends on delta t. So because its delta is increasing, but the number of healthy gates here can never be larger than that's controlled by this part. So in this regime, we expect the number of healthy gates to stay constant. In third regime, when delta is larger than say t star 1, but is less than t star 1 plus t star 2, we see that actually as delta increases, this part starts to decrease, and it decreases in this way. It will decrease linearly in delta. At the end, the fourth regime is when delta is much larger than t star 1 plus t star 2. When you draw the circuit picture, it should be clear that there are basically no more healthy gates. And so this is just a very rough qualitative circuit analysis. One can make all of this more precise, again, by considering some version of 6-point functions. This is discussed in this paper, but I won't go into the details here. So we see that there are 4 different regimes from circuit analysis. How about the bulk? And in the bulk, there are 2 different effects happening. The first effect gives rise to the growth of post-collision region. What will happen is that as delta increases, the collision point will get closer and closer to the bifurcating surface. So this point will go down, and this will cause a post-collision region to grow. The second, and if we ignore the back reaction and let's say estimate how large this is, let's say maybe from space-time volume or various quantities, roughly speaking, it grows linearly in delta t. The second effect gives rise to the shrinking of a post-collision region, is that as the collision energy increases, eventually we will have to take care of the back reaction. And the back reaction will cause the singularity to bend down, and this will make the post-collision region shrink. In this case, you will see that, so let's say if we just assume this collision point is already very close to the bifurcating surface, basically we're interested in this entire shared region. It will first decreases in delta t linearly, eventually it becomes exponentially in delta t. And at the end of the day, what happens in the bulk is a competition between these 2 effects. When delta t is small, the first effect will dominate, correspondingly the number of healthy gates in the overlap grows linearly in delta t. Of course, that corresponds to the circuit part where the number of healthy gates in overlap grows linearly in delta t. And eventually, when delta is large enough, the first effect is negligible, but the back reaction becomes very important. And correspondingly, number of healthy gates in the overlap will first decrease linearly in delta t, and eventually becomes exponentially small in delta t. What's interesting is that there can also be intermediate regime where the 2 effects basically exactly balance out each other. And this actually corresponds to the case we discussed earlier that for certain time window, the number of healthy gates in the overlap region can actually stay a constant. I mean, it doesn't change as we vary delta t. So this is just the qualitative picture, but we can make this. So for the case of ADS-sized black hole spherically symmetric perturbations, the post-collision geometry is worked out, and we can actually do a detailed comparison. So this plot is the case, is a comparison between the circuit model and some bulk calculations. In the circuit model, we estimate the number of healthy gates in the overlap region. In the bulk calculation, we computed a space-time volume in the post-collision region, and we take log S to be 36. There's a linear increases, saturation, linear decreases, stays small. And this plot is basically a time derivative of the first plot. And we can also make log S larger. And as we make the separation between square boiling time and thermal time larger and larger, I mean, the plot looks better. So at the beginning of the talk, I mentioned that we want to, in particular, we want to understand that for two different cases, it's either the signals come from different boundaries or the two signals come from the same boundary. We want to say that they more or less should interact in the same way. And let's look at a case where the two signals come from the same boundary. Let's say we start from thermal field double and we send in a perturbation. So from right at time t2, then we go backward in time and send another perturbation at time t1, where the time separation of t1 and t2 is again given by dot t. And if you draw the quantum circuit, you will see that the quantum circuit picture is actually very similar with what we just discussed before. The two directions of quantum circuit correspond to future and past time evolutions. And we have two perturbations, they grow in opposite directions in one shared quantum circuit. In particular, because they have a similar quantum circuit, one would say that if we again ask the question of what's the number of healthy gates in the overlap region as a function of delta t, they should be very similar as what we discussed before. So from the bulk side, we see that when delta is small, they basically just collide in the exterior, and this region grows linearly with delta t. And when delta t is large enough, the collision actually happens behind the event horizon. And in this case, one can again argue that this region will actually first shrink linearly, later exponentially in delta t. So the bulk picture is very similar for delta large enough. The healthy gates are again stored in the post-collision region. So one sees that there are some universal features, at least when the collision is strong enough such that it happens behind the black hole horizon. Basically, the shrinking of post-collision region has to do with the fact that there are no more healthy gates in the quantum circuit. So for the two different cases, the two signals come in from different boundaries or come from the same boundary. The underlying boundary mechanism, that the way they interact is essentially the same. So when I started this set of projects, what I had in mind was ER equals EPR. But later I realized that actually it can be more general. What we see is the boundary mechanism describing how matter gravitationally interacts, that we have perturbations overlapping in the shared quantum circuit. In particular, one can apply this picture to one-sided black hole, of course, assuming there is interior geometry. For example, black holes with end-of-world brains. So then there comes a more ambitious goal. Can we derive gravitational interactions, at least approximately, from knowing properties of the quantum circuit? And the immediate question is, what's the right bulk quantity to ask about? I will come back to this question later and ask you guys for opinions. But before that, so let me briefly discuss localized shockwaves, the collision between localized shockwaves. The localized shockwave, with one shockwave, localized, the geometry was worked out in a beautiful paper by these authors. So roughly speaking, we still have a shift along the horizon, but the shift will be transverse position dependent. So we call this shift h of x. And this is the circuit picture. This picture, I basically took this picture from their paper and redraw it. It's a figure 1 of their paper. So they introduced, there are two cones. One is this one. This one is the causal light cone. The other one is the butterfly cone. This causal light cone has slope 1, but butterfly cone has slope VB. Generically speaking, is less than 1. So what will happen is that the operator will spread inside the causal light cone, but its effect stays small until reaching inside the butterfly cone. So the quantum circuit is roughly like this. And in this case, the vertical direction indeed has meaning. The vertical direction is a transverse direction. And if we want to consider the collision of localized shock waves, we put two such circuits together. And what we will do is that we will focus on some particular x, let's say particular x. And so these are labeled coordinates of this time, spatial coordinates, time spatial coordinates. And with slight abuse of language, we will call the distance. Let's say at a particular x, we'll call the distance between causal light cone and the butterfly cone. At a particular x, we will call this T star. And again, we will assume in this case, T star 1 is larger than T star 2. Actually, the reason that we had to consider different scrambling time is because for localized collision, generically, unless we have head-on collision, and this so-called two scrambling times will be different. So let's again first do a circuit analysis. We will fix the impact parameter, but vary the time separation. It should be intuitively clear that if the time separation is really large, then the two guys just never see each other and propagate freely. But once we make the time separation smaller and smaller, and eventually this delta x will become positive, where delta x here is the time separation of its causal light cone at a particular spatial location x. Again, for the regime 1, when this one is less than T star 2, and we see that this part grows linearly in time, we expect the number of healthy gates at a specific location x grows linearly in delta of x. The second regime is when delta of x is between the two scrambling time. And if you play with this picture a little bit, you'll see that as you move this pink wedge, actually this part stays constant. The third regime is when delta x is larger than both of the scrambling times, but less than the sum of the scrambling time. Then we see that number of healthy gates at location x in the overlap region actually start to decrease with delta of x. It decreases in this way. The fourth regime is the case that when the delta x is so large that if you draw a constant x slice, you realize that there can basically no more healthy gates. So to briefly summarize, what we have is that if we focus on particular x, in this case, we still get, roughly speaking, 4 different regimes: linear increases, constant, linear decreases, and basically very small. The bulk calculation is more subtle because the metric in the post-collision region is in general unknown. Actually, from the circuit analysis, one should be able to see that, I mean, there is not very good symmetry if there is a solution. So what we will do is that we will instead identify different bulk features that give rise qualitatively to those different behaviors. So let's first look at the growth of post-collision region at specific constant x. So when most people in the past, when people study localized, so when people study shockwaves, they normally consider that the shockwaves comes in at a very early time, such that it basically lies on the horizon. But for our purpose, in order to study the growth of a post-collision region, we actually need to assume, we have to assume that the perturbation comes in at finite time. The first question is, where is the shockwave? And at first, I made some guess that turns out to be wrong. The first guess is that, okay, so if it's at the horizon, it's given by u equal to 0. But maybe away from the horizon is given by u equals constant. But this is not right because this violates causality. And later, I was thinking that maybe this thing will propagate away with butterfly velocity. And then I worked out some explicit examples and noticed that this is also not right. In fact, in planar BTZ or hyperbolic black holes, the intersections of the shockwave surface with the boundary is exactly the causal light cone. So essentially what will happen that if we draw a constant x slice and away from the source, the signals will be delayed. But if you ask where the shockwave lies, it's delayed by amount which is controlled by the distance to the source. The butterfly velocity doesn't appear here. What appears here is the causal light cone. So from this point of view, we see that as we make delta x larger, and this part, basically, if we ignore back reaction, then it's exactly as what we had before. We expect this region at a constant x slice to grow linearly in delta of x. So this is basically the first effect we discussed before. The post-collision region grows linearly in delta of x. And if we want to study the shrink of post-collision region, then we have to include back reaction, but we don't know the geometry. So instead, I want you to focus on one particular quantity that I find interesting. Recall that this H1 of x and H2 of x are the amount of shift on the horizon. And in fact, if you the expression was worked out by other people, and if you take their product, it's actually exactly given by e to the del t of x minus t star 1 minus t star 2. Again, I remind you that this quantity definitely depends on butterfly velocity. Butterfly velocity doesn't depend on here, but butterfly velocity will occur here. So if from a circuit point of view, this quantity actually characterizes the amount of overlap in the circuit at location x. But on the bulk side, this quantity, this product controls the nonlinear effect in GR. So if we trust the circuit model, we can make predictions on GR result. So circuit model will predict that the singularity will bend down and the shared interior region eventually becomes small at transverse locations x, where H1 of x times H2 of x becomes of order 1. And I find it reasonable because this is what the nonlinear effects of GR becomes important. So one can do some explicit calculations, but I figure out it probably won't be too interesting to go over the technical details. What one do is that one can look at the jump of expansion across the certain shock waves, and one can apply retardatory equations a couple of times. So at the end of the day, what we will see that, so once you go across a shock wave, no matter you are at the source or away from source, the expansion will jump. And corresponding, and if you apply retardatory equation again, that will put an upper bound on the affine parameter, on the affine distance here. So in particular, when you have, let's say, two colliding localized shock waves, so L1 is the affine distance here, L2 is the affine distance here. The product of these two affine distance will be upper bounded, roughly speaking, by 1 over H1 of x times H2 of x. And as you all know very well, that this light-like affine distance depends on the normalization factor. So what we do is that we normalize the two tangent vectors v1, v2 such that their inner product is -1. Then one can unambiguously say that the product of this L1, L2 is upper bounded by this quantity. Then qualitatively, it should be sort of reasonable to see that if this guy becomes really large, then this one will become small, then somehow more or less this one is upper bounded by, the whole large post-collision region more or less cannot be too large. But of course, if we don't put any additional assumptions, if we allow arbitrary geometry, we cannot say anything because this part can be arbitrarily large, even if we upper bounded the product of these two. But we do know that the geometry cannot be arbitrary. It will satisfy Einstein's equations in a vacuum with the negative cosmological constant. So what we did is we did a really naive estimate. Let's focus on one constant x slice. And we just assume the geometry is ADS2. And we know that if we assume the product of this L1, L2, then what can we say about area in this region? And miraculously, in this case, what we see the area in this region actually agrees exactly with the quantum circuit prediction. When delta of x is less than the sum of two scrambling time, it goes like t star 1 plus t star 2 minus delta of x. When delta of x becomes large enough, it eventually decays exponentially small in delta of x. I mean, I have to admit that this is a rather bad estimate because it's far from rigorous proof, but I more or less find it reasonable. I hope we can improve it maybe in the future. So to summarize, for this case of localized perturbations, we compare the circuit analysis and the bulk geometry. From the circuit analysis, we have 4 regimes: linear increases, constant linear decreases, then stay very small. And when we compare with the bulk, we more or less get a first part. We modulo some unjustified assumptions. We sort of convince ourselves about this regime and this regime. But this part, let's say how these two effects completely balance out, I have no idea. Without knowing exactly the geometry, I don't know what to do. So some future directions, I mean, hopefully one can do some better bulk calculations, estimations. I'm afraid eventually, if one really wants to do this, one might need numerical relativity. And another thing that we should be able to quantify the circuit picture by either some 6-point function, or maybe these days there are some other definitions of complexity or size that might be useful. It will be interesting to explore. So before I end my talk here, before I end my talk, I really want to use this workshop as an opportunity to ask you guys for help on one question that has bothered me for quite a long time. So what we want to do is that we want a boundary interpretation of some bulk phenomena. We want a boundary interpretation of bulk gravitational interactions. And we thought we find a boundary mechanism, which is about this overlapping perturbations in the circuit. Then I suddenly realized that I don't even know what's the right bulk quantity to ask for. So when I first thought about, okay, bulk gravitational interactions, the first thing that came to my mind is Newton's law, G(m)(m)r squared. But clearly, it won't work in this case. We're considering high energy scattering. And as for scattering in flat space, in the past, people mostly consider S matrix, where you define incoming state and outgoing states. But in this case, the collision happens completely behind the black hole horizon. So what's the right quantity to ask for? I mean, if S matrix or scattering amplitude still works, then it will regime. And we do know that later the post-collision region will become very, very small. I'm not sure if S matrix or scattering amplitude still works, but when it works, it will regime. There are some recent interesting discussions in this paper. And so far, what we have done is that what the quantity we look at is the space-time geometry after collision. But clearly, this is not a conventional quantity one usually uses to characterize a collision process. So can one make a connection between this and the more conventional characterizations of scattering, maybe improper regime, or maybe this may be completely crazy? Can one define all states by treating the singularity as another boundary? This may be totally crazy, but it's just I have no idea. We have a boundary mechanism, but I don't know what's the bulk quantity to look for. And so if any of you have ideas, I'm really happy to talk to. At the very end, I'll point out some unanswered questions. First of all, singularity is always an outstanding unsolved puzzle there. The existence of spacelike singularity prevents the meeting of signal that is sending too late. But what about collision near the inner horizon of a charged black hole? And I don't think I just understand that region near to the inner horizon in any way. And how to make this picture of a black hole interior has unitary quantum circuit more rigorous? What's the similarity or difference with tensor network in the exterior? And how to connect this picture with other discussions of black hole interior. Let's say there's some other interesting papers. Another thing I sometimes get frustrated with is that there are all these interesting discussions about the black hole interior from different approaches, but probably because I don't understand any of them well enough, I don't see any connections between them. So that's something I hope to understand better. And throughout this work, I had a fixed Hamiltonian in mind in the context of ADS-CFT. Then how to incorporate different states of baby universes. There's some interesting papers recently. And we have been trying to understand matter propagating in the interior, ordinary matter propagating in the interior in terms of quantum circuit, and how far it was. So yeah, that's all I have. Thank you.
Questions?
Probably have a limited question, like because your circuit is just 2-dimensional, right?
Yeah.
And you can identify the number of the quantity, but identify the number of healthy gates. Right?
Yes.
But how? But in the gravity side, if we consider higher dimensional black holes, if you are still in this, consider the area, or is it
you notice that I actually focus on particular X slice. I would say that if I know the geometry well, I will compute the first quantity I will look at will be the space-time volume. But again, we can do this as an integral. We can compute it slice by slice and do the integration.
Yeah, I see. But more subtle questions like if you have like a collision from a different angle, for example.
A different angle. Here we're considering we are not considering head-on collision. We're considering things like this.
Yeah. Oh, okay.
Yeah. So it's we didn't assume. So it's non-zero impact parameter.
Okay, I see. But how does you enclose a space-time, because you are.
So in the current work, what we do is that we basically look at the constant X slice and see what happens at the constant X slice. And on the gravity point of view, there's a quantity called h1 of x times h2 of x, which basically gives you the back reaction on this constant x slice. And that quantity from circuit point of view is essentially tells you how large the overlap is in the quantum circuit at a constant x slice.
Questions?
I don't have a question, I have a comment. I actually remember your talk from last year and I just wanted to say I really like this one, so great job.
Thank you. I really hope someone could tell me that what's the correct bulk quantity to look for. I've been struggling with this for so long. Hi, Daniel.
Well, yeah, maybe just a thought about that. I mean,
Oh, great.
probably not a helpful thought, but I mean, probably that's only something that approximately makes sense, right? If you want to talk about, some sort of S matrix or observables that you compute in the black hole interior.
That's true.
Maybe we could hope that in the limit where the entropy is very big, that there's something like an S matrix to some approximation,
You mean black hole entropy is very big?
Yeah.
Yeah, yes,
Yeah,
yes.
but I mean, but then there will be some sort of irreducible ambiguity. I don't exactly know whether it'll be suppressed by powers of S or e to the minus S. Maybe it depends what you ask about.
Yeah, I don't know. So my hope is that there might be certain regime where S matrix or scattering amplitude is still useful. But in that regime, I hope to make a connection with the quantities that we have a control of in the circuit model, like the post-collision geometry with those more conventional quantities. That's one aspect. Another aspect is that I feel like eventually S matrix or scattering amplitude will not be useful when collision becomes really strong.
But it'll just be approximate. I mean, I think the question is, are there any observables in the interior which are exact, precisely well-defined? And I would guess no. Right, and so I mean, maybe there are. That would be amazing if anyone knows any. But then once we accept that they're only going to be approximate, then maybe
Yes.
the S matrix is good enough. Maybe there's an approximate.
Okay, how do you define outgoing states?
Well, you define them approximately by not. Right. I mean, yeah, I can't give you a precise definition in terms of asymptotic wave packets or something, right? But
Yeah,
I can say it's. I mean, you could build the LHC back there, right?
build LHC inside interior.
Yeah.
Yeah, yes, one interior is not enough.
And there's some data that, I mean, the LHC also doesn't measure the S matrix, right?
Yeah.
But it measures something that's, well approximated by the S matrix because, the size of the LHC is very big compared to, the Fermi scale or something, right?
Yeah, one thing maybe I also don't know this S matrix scattering thing well enough is that I thought it's defined with respect to asymptotic flat space. But when the space-time geometry is significantly changed, like the post-collision geometry is significantly changed.
Yeah.
Can you still define the
Yeah,
outside?
I mean, so formally, no, right? But on the other hand, like we think we live in de Sitter space, but we still use the S matrix at the LHC, right?
You are basically saying that if we ignore back reaction, then just we ignore change of geometry and just treat that portion as a flat space, that we can use S
I mean,
matrix,
it's
right?
some approximation, right? I mean, this
Yeah.
is an inherently not a super well-defined.
Sorry,
thing.
to jump into the discussion, most experimentalists at the LHC don't really know de Sitter space, haven't really taken courses on the topic, so they would not be measuring that or anything like that. That's why they use the S matrix.
I mean, they really measure some energy correlators in some calorimeter or something is what they really measure, but we can call it.
Yeah, I agree. I mean, this is very much like a recent proposal by Lampers and Pingao in their recent paper. They basically just discuss the out states they define the outgoing states by basically preparing the state only from the exterior and evolve it to the interior. I mean, my guess is that, yeah, it will work if the collision is very mild and basically you can ignore the back reaction. But my question is that I think what I find interesting, what's happening behind black hole horizon is that is the different aspect that the geometry has to be completely changed. Then what do you do with that?
But that's true in de Sitter space too, right? And yet we live in de Sitter space and we use the S matrix at the LHC, right? So I mean, yeah, I don't know. There's some. I mean, I guess the question is there some interesting question that's not captured within, whose answer is not captured within perturbative general relativity coupled to effective field theory? you know, that you can study in the CFT, right?
I have a question. Question. Ying?
Yes, Danny.
Supposing the energy, there's a range of energies of a collision, which is both low enough in one sense and high enough in another sense. It's high enough that that the collision should create a black hole,
Yes,
but it's low enough that the black hole radius is much smaller than the interior geometry itself.
oh, yes, okay.
Can you see that a black hole forms from the circuit analysis? What is this? Does the circuit analysis in that range give any hint or indication that something like a black hole forms on the interior?
I don't know the answer. Good question. Actually, another thing I'm interested in is the circuit understanding of the formation of the black hole. So far, it's the entire perturbation. We already have a black hole, then with small perturbation, but I don't know. I don't have an answer. I don't have circuit interpretation for formation of a black hole.
Mhm.
So for what we have is that basically we know that there is a transition behavior, let's say after one scrambling time. And so it's going up, going down, then stays exponential small. So after this going up at one scrambling time, that's where the collision energy reaches Planckian energy. And so after that, what we see, because you already have a black hole, so what you will just see that the post-collision region grows, then start to decrease. So the transition happens when the collision energy reaches Planckian energy. I don't know if I should call that's roughly speaking like a form a new black hole. Yeah, I'm not sure. I don't know. I hope the answer is yes, but yeah, it's just that's all I see with already when we already have a black hole sitting there. I mean, I hope to understand a case where we didn't start with a black hole, but I don't know how. Yeah. Well.
Yeah. So one interesting question when you have the singularities is the extent of time, the maximum time that you have between perhaps the collision and the singularity.
Yes. Yeah, that also decreases. It's so what I find is so far what we estimate is roughly speaking is this extent. And this thing also decreases, probably in slightly different way. Eventually it becomes exponentially small. So it's, I mean, this thing and this thing are related, they're a function of each other. But it's the question is, so with circuit model or with Einstein's gravities, we can give various descriptions about the space-time geometry in the post-collision region. But what I want to say is that this is not normally the conventional concept people use to study a scattering process. So yes, we can put a bound here, but so what else can we say about that?
I mean, I suppose something a little better than an S matrix is you can study these dressed gravitational observables where you go in from it, along a geodesic from the boundary and then measure a field, right? So that's something that knows a little bit more about the geometry than just the S matrix, which really only makes sense when everything is very small compared to the radius of curvature. So that'll work when when you measure things whose size is comparable to the radius of curvature.
Yeah.
But it'll still only be approximate, right? I mean,
I'm fine with approximation as long as we know what quantity to go for.
yeah. So that's at least something.
I mean, there's a setting where you might hope to answer the question, which is not a real black hole, but like an ADS-Rindler black hole.
ADS-Rindler black hole.
Yeah, which is kind of a fake black hole, but then you could do exactly what you did
Yes.
in that setting, quote unquote, behind the horizon.
Yeah.
And there we think we kind of understand what that S matrix
Yeah.
means.
Because the signals eventually come out to the boundary. Yeah.
Yeah, so, but I'm wondering if you could take a lesson from that to
That's
the case
interesting.
where a real singularity does form.
Yeah, that's interesting. Thank you. Yeah, I don't know. It's that will be a nice setup, but it has a property that things
Yes, I
eventually come out.
understand
Yes.
cheating, but
Yeah, yes, but thank you. Yeah, that's interesting.
But I think especially in that case, if you still want to follow Juan's suggestion to measure distance to singularity, then there is no such a definition.
Oh, actually, you can look at, let's say, for example, in ADS2, then you can look at the distance to the inner horizon. I mean, of course, ADS2, there's a no sense singularity bend down, but the distance, the proper distance to the inner horizon behaves similarly, decreases, eventually very small.
Sorry, I have a very basic question. So when you talk about the collision behind the horizon,
Yeah.
do you assume that there is some infalling observer who measures this collision or what? Or you think that this is?
I would imagine that if there was some observer sitting there, he will see something like this.
But then how?
I don't know, good question. So that's why I was asking what's the right bulk quantity to ask for.
Okay, I think we're out of time, so.
Okay, we can talk later.
Thanks.